Yeah, so hello everyone. It's a great pleasure to be here. I've been working on this project for the last 4 to 5 years. And yeah, it's called Marco, and it's an MLIR-based compiler for a DSL named Modelica, of course, as the name suggests. And yeah, first of all, a little bit of introduction and motivation to the project. And let's talk about the DSL first. So Modelica is an acausal and object and component-oriented language through which you can describe a system of differential and algebraic equations. For example, let's say that we want to describe a capacitor, and we can do that by describing each of the two pins and through the concept of connector. And then what we can do is to connect those two pins, describing the equations that govern the system. In this case, the physical laws of the capacitor. And then, of course, you can add other components to the system and make more complex scenarios. I'd like to highlight two things about this code. And first is that you can see an unusual operator, which is the time derivative operator. And second is that the free equalities consist of equations and are not assignments. There is no enforced order between those three equations, like you would naturally write by hand, and assignments are indeed not explicit. And in other words, Modelica is a declarative language. It's not a programming language. As such, the following code does not semantically represent an iteration, but rather a simultaneous declaration of multiple equations, in this case 100. And that will turn out to be very important for the talk. So, but first also, why are we building a new compiler? Well, it turns out that the last feature that I was mentioning is not very well handled by mainstream compilers. And what they do is to unroll those declarations and apply the DAE algorithms to the unrolled version of the source code. And this is what they would end up having within their representation. And even though unrolling may have beneficial performance at runtime, what happens is that it has a very terrible impact on compilation performance, and compilation times quickly become unfeasible. And by unfeasible, I mean like they are taking days of time. So and also you get exploding binary sizes with like gigabytes of executables. So the main motivation of Marco is to go beyond the current algorithms for the AE system and devise new ones that are able to reason about array variables and the loops of equations. So I will call them just array equations. And with the goal, more in detail, is to be able to simulate large-scale systems, which are indeed represented often by this construct. Well, why MLIR? I don't think I really need to convince you about why are we using MLIR, but anyway, so the benefits are, of course, the reuse of an open source IR infrastructure, as well as having the reuse of concepts and optimization that are shared across different domains. We also have tighter integration with the LLVM backend, and possibly easier code generation for custom architectures and better debuggability. I will not go into the details of all of this. I guess you already know all of them. But let's see instead how is the architecture and IR of Marco made. So the structure is quite typical for an LLVM compiler. So we have our front end, which processes the Modelica code, which then goes into the middle and backends of LLVM, and finally gets linked to the libraries composing our runtime system. And however, Marco is also integrated with the Clang driver with the goal of receiving target and optimization specific information, and also reuses the front end of Clang for C code, whose usage is allowed for the implementation of external function by the Modelica specification. For what regards the compilation pipeline within the front end of Marco, the compilation is divided into three main parts. First, we have some canonicalization passes, which address some language-specific features and allow for certain assumptions later in the pipeline. The second part covers the mathematical aspects of DAE processing. So, for example, it performs causalization, where many of the new array-aware algorithms live. and apply, for example, also numerical integration to the system. And finally, the last part is more traditional in some sense and applies some optimizations and lower the various dialects to LLVM. And then we, as I was saying, we give it to the middle end and back end of LLVM. Of course, there are also many other passes, like potentially with all optimization enabled. As of now, the frontend has a total of 85 passes, but of course, we are not going to see all of them now because it makes no sense. It's impossible with the time we have. But throughout the pipeline, however, you see that we have some new dialects on the left. So I'm gonna now introduce you to them a little bit. I will not also not go into detail of them. I will just highlight instead why certain decisions have been made, which may be beneficial to the community. So the most relevant dialect is surely the B Modelica one. So you may wonder why the B. So actually, Marco, as of now, doesn't really accept Modelica code, but rather a subset of the language, which is called base Modelica, and from there you get the B. And the Modelica code is actually given to another compiler that removes object orientation, and Marco then starts from there. Potentially, it can be done everything also inside Marco, but we don't have the manpower as of now. So the main concept, the purpose of the base Modelica dialect is to represent differential algebraic systems of equations. So the main concepts that are captured by the dialect are, of course, the one of the model, and we do that by just having a single region operation with a name, and within that region we actually describe variables and equations, which are less obvious to represent. So what about variables? In case of variables, we have an explicit design goal to preserve interoperability with other dialects. Why is this goal really so explicit? Well, you may know that some operations within the MLIR ecosystem may have the so-called isolated from above trait, which prevents the inner operation of that operation, so the ones within its regions, to actually reference SSA values that are defined outside. And so if we want to really be open to any possible other dialect that you may use within the IR, then we have to take this into account. And the solution to this is just to adopt symbol semantics for the declaration of the variables of your model. And we have some bridging operations that merge the two words when you need to shift from symbol semantics to SSA semantics. And then those operations, and like the declaration of variables and the bridging operations, are lowered differently according to the place where you use them within your IR. For example, in case of models, you just get global variables, and if you are instead declaring variables inside your functions, you just get allocations, which optionally that get optimized, of course. The representation of equations is also not immediate, considering the goals of Marco and the transformation that IR goes through. The idea is to avoid code duplications since the beginning, because actually the result of some analysis may depend on the indices of that specific equation. Remember that you have array equations with an iteration space with multiple indices. And to achieve this, the equation body has been split from the actual instantiation. So we call the first the equation template, and the latter we call it the equation instance. As you see from the example, like an equation template is parametric on the indices, which are specified by the instance, and also the indices are backed by an RT implementation, an in-house developed one, which is very efficient for like compacting the range of indices. And also in this case, we prefer SSA semantics instead, differently from variables, because we have complete control of the IR structures, and so the nesting problems are not there anymore. Also, we have some additional dialects, which I will just go very quickly through them, but it's good to see them. So we have 3 dialects called IDA, Kinsol, and Sundials. So their purpose is to integrate with some external solvers, in this case IDA and Kinsol, which are part of the Sundial suite. And they are used during the model solving stage, so the middle part of the compilation pipeline, and they are used for either providing a BDF integration method or to numerically solve algebraic cycles that are still there within the system. So just a quick example of how the EDA direct is made. The Kinsel one is almost mirroring that. So we have an instance of the solver, which we declare for the instance operation, and then we inform the EDA object about the variables and equations. So in this case, you can see we are informing the runtime that there is a variable, a differential variable, and we give also some callback functions to actually get and set its values. And similarly, for equations, we adopt a similar mechanism of functions, and we give the callbacks to them. Okay, and we also have automatic differentiation to achieve those, to obtain those functions. So we have a residual function and a partial derivative so-called function that is used to compute the Jacobian metrics of the system. But yeah, and finally we have the runtime direct, which interfaces with the runtime. The runtime direct which interfaces with the runtime environment of Marco. It provides some support functions, such as the implementation of sine, cosine functions, but also expects some it is used to provide some callback functions that the runtime environment will expect to be there by the compiled model. So I've gone a little bit fast through that, but I would like to showcase one of the optimization examples that we have within our pipeline, where you will see two of the directs that I've been talking about. So the idea is to parallelize independent sets of equations. So imagine that you have this dependency graph, okay, where you have, for example, that equation 1 can be computed only if you have already computed equation 0. And what you can do is to compute a dependency graph among the equations and understand that, for example, all the equations within group 1 can be computed parallelly in an independent way. And this may seem like naive and inefficient because you say, okay, you spawn 2 threads just for 2 equations. But yeah, I recall you that maybe these 2 equations are array equations, and they may be also independent one from another. And so what you can do is to actually split all of the ranges and give them all the equations to multiple cores. And this is the main idea, not very complicated. From the AI perspective, what we have is that if you consider that simple example, you have some opaque blocks where you have just knowledge about the dependencies, so which equation is writing to which variables and needs which other variables. And you have an additional attribute saying if the schedule block can be parallelized together with others. So first modification is that we apply that dependency graph and we wrap the groups. So the parallel schedule blocks operation just represent the groups that I was showcasing in the previous slides. And then what you get is that you apply a specific transformation to look into those opaque blocks if it can, and if it's able to do that, then it instantiates some runtime scheduling objects that are managed by the runtime system, and those will be actually the ones in charge of dispatching equations, splitting the indices and dispatching the equations among multiple threads. And yeah, just one example where you see the performance of the project. So let's consider this thermal model of a silicon chip. It's a very simple model, and don't expect anything like super complicated. So you parameterize your chip in 3 dimensions. You can control the number of volumes according to those 3 parameters, and you get a fixed power source at the bottom and a fixed cooling surface on the top. And we have employed the explicit Euler method, and we measure the compilation time and simulation time for a Marco and another solution, which is the Open Modelica Compiler, which is open source. And what you see is so you see these are the compilation times on the left and the simulation times on the right. What you see is that Marco really excels at the compilation times because it takes advantage of those array-aware algorithms during compilation, and it has basically a constant time compilation time, which is very different from Modelica, for example, but also other tools. And simulation, time-wise, you get some considerable benefit, and also you notice at some point you have an automatic multi-threading activation from the runtime system, because it understands that at some point while you are scaling the system, it becomes beneficial to activate your dispatching to multiple cores. So conclusions, just to sum up everything. So current status, okay, it's still a prototype compiler, okay, so it has been going on for 5 years, but there's still work to do. So we are, for example, we're very interested in going to custom architectures, but even just GPUs, for example, it would be a very good thing, especially for the use case of Marco. And I would like to conclude with a few things that may be very well interesting for the community. So I've been encountering a few difficulties throughout the development. And first of all was the integration with the Clang driver, which is not exactly easy to work with, because it's a big code base. In some sense, it's not. I think it may be structured a little bit better in some points, and some copy pasting was also required. And still, we have some question about how to handle source modification. Also, symbol tables of MLIR, they are nice, but they need to be manually updated, and some points in the pipeline were scaling quadratically, and those points have been fixed, but yet I'm wondering, like, can we maybe do better? Can we, for example, attach automatically the symbol table through a tray to the operation and have the infrastructure to automatically update them? Just wondering. And yeah, also last few things, really, we would be very interested in developing some interface-based mechanism to have a cost model for operations, because the automatic grouping of parallel independent equations is very naive at the moment, but we would like to consider how much, like every equation, like how much does it how heavy it is with respect to others, and so that we can better balance computation across multiple cores. But this brings us many questions. Here you can see just some of them. And early access, this was more of a problem within the very first few days of development. But I mean, I know some work is going on, but in Marco at the moment it's addressed, and we are fine at the moment. Yeah, so thanks for your attention. Here you have your QR code to the project if you want to visit it, and we are very much welcome to contribution if anyone wants to join. Thank you.